So F1 is the force exerted by the ball on the hands of the cricketer. So which is equal to change in momentum by time. Change in momentum we know which is mu, and time is, let's say, t1. So this is the force exerted by the ball when the person doesn't pull his hand. When the person doesn't pull his hand, then the ball comes to stop immediately. So that means t1 is small. Another case, when the person takes longer time to catch the ball, that means the person pulls his hand. Whenever he does that, then the force exerted by the ball on his hand would be mu by t2. Here t2 is another time when the person pulls his hand, and t1 is the time when the person doesn't pull his hand. So t2 is more compared to t1. So in this case, see, this F and T has inverse relation. This force and time has inverse relation. If time taken is more, then force exerted will be less. Therefore, when the person pulls his hand, it takes longer time for this change in momentum. Okay, so longer time for this change in momentum. That means time is more and force exerted by the ball on the hand will be less. Because of that reason, the person pulls his hand while catching the ball. Athlete often lands on sand after taking high jump. Yes, if the athlete lands on the cement floor, then what will happen? The athlete will come to rest immediately, instantaneously, okay, in a short interval of time. If the time is less, force exerted by the feet on the floor will be more. But if athlete lands on a sand, then it takes time for the athlete to come to rest. Okay, the time interval is more when it lands to the sand. Therefore, what happens? The force exerted on his feet decreases. Okay, so similarly, there is another example, 3 example. You can say it on your own. And these numericals which I asked you to do it, I think you have done it. Now Newton's third law of motion. Newton's third law of motion is also very important and easy one. Newton's third law says, to every action there is always an equal and opposite reaction. To every action there is always an equal and opposite reaction. What do you mean by that? Let me explain it by the figure. We have a book. Let's say this is a book which is lying on a table. So there's a force acting downward, which is the weight of the book. Okay, this is the book which is lying on the table, not moving, just lying on the table. It is at rest, and there's a force acting on this book which is acting downward, which is the weight of the book. Weight of the book is acting downward. If only, which we call it action. Okay, weight of the book which is acting downward, we call it action. If there was only one force, then the book should move downward. Since the book is at rest on the table, there must be opposite force acting upward. Okay, and that opposite force we call it force of reaction. Okay, because of that force of reaction, the book is not moving downward. Now force of reaction has to be equal to the force of action so that the book will be at rest. If the force of action which is acting upward will be more, then the book should move again up. But book is neither moving up nor moving down. Therefore, force of action and force of reaction has to be equal. Therefore, Newton said that to every action there is always an equal. Force of action has to be equal to force of reaction and opposite reaction. There should be opposite reaction. In the sense, force of action is acting downward, force of reaction is acting upward. So this is the Newton's third law. Okay, and there is another example. When you push a wall, you exert a force on the wall. So when you exert a force on the wall should exert, that is called action. The wall should exert force on your palm. Okay, that is force of reaction. And this, whatever the force you apply, that force of reaction will be exerted by the wall on you. Therefore, if you push it harder, the wall will push you harder. Motion of a boat moving away from the shore. When a boatman wants to move the boat away from the shore, what does he do? He pushes the shore by a bamboo or oar. Okay, that is action. So he pushes the shore by a bamboo. When he pushes the shore, you are applying a force of action, and that shore pushes the boatman back. Okay, pushes the boatman away with equal and opposite force. Equal and opposite force, which is called force of reaction. Because of that reason only, the boatman moves away from the shore. So firing of a bullet from a gun. When a man fires a bullet, then the gun exerts a force of action on the bullet. Okay, because of that, the bullet starts moving this direction. When a person fires a gun, the gun exerts a force of action on the bullet. So force of action on the bullet is this way, and the bullet should exert equal and opposite force on this gun, and that is force of reaction, which causes the recoiling on gun. So gun recoils whenever the bullet comes out from the gun. This bullet exerts equal and opposite force of reaction, which causes the recoiling of gun. We have also one example which is called rocket motion. Okay, rocket motion. See, you can see when the rocket just before the motion of the rocket emits gases. Okay, it emits gases. These gases, so rocket exerts force on the gases, which is going downward, and this gases exerts equal and opposite force of reaction on the rocket, which is called the force of reaction. So force on gases, we call it action by the rocket, and force on rocket by gas, we call it force of reaction. Because of force of reaction, the rocket lifts up. Okay. Okay, motion of a man. So when the person moves forward, what happens? This toes, what is it called? Yeah. When a man applies a force backward by his foot on the ground against the force of friction, yes, you can see here the man is applying force backward. Okay, man is applying force backward in this direction, so force of reaction will be acting this one direction. Therefore, the person can walk on the ground easily because of the force of reaction. Okay, the one thing you have to understand over here, let me read one by one. There are some technical terms over here. When a man applies a force backward by his foot on the ground against the force of friction, the ground exerts an equal and opposite force, which is called reaction. Just now explaining that. The horizontal component of the force of reaction enables the man to move forward. This reaction is acting this one, and force is acting this one backward. And there are two forces, no? If you can see, we can find the horizontal component of this reaction force towards this direction, okay, and vertical component towards this direction. This horizontal component of this reaction force helps the person to walk forward, okay. And obviously, it will be difficult for a man to move on a slippery road where friction is less. If there's no friction, then the person it would be very difficult for the person to walk because there's no force of reaction. Okay, it would be very difficult. There's no force of reaction in this direction. Okay, while catching a ball, the ball exerts a force action on the palm of the cricketer, and the cricketer exerts an equal force on the ball to stop it. That's called reaction. Okay, so action and reaction takes place simultaneously. And one thing you have to understand over here is that action and reaction do takes place simultaneously, but it takes place at two different bodies. Okay, action and reaction takes place at two different bodies. Here you can see it's written over here. Action and reaction never act on the same body, which is true because in this case the action is done by the weight of the book and reaction is done by the table. So your two bodies are book and table. Okay. Similarly, in case of firing of a gun, we have action due to the force exerted by the gun on the bullet and reaction due to bullet on gun. So we have two bodies. So action and reaction, you can see all the examples. We have chosen two things, two bodies. Then they will never act on the same body, but they will act simultaneously on two different bodies. It will act simultaneously, okay? It will act simultaneously on two different bodies at the same time. Simultaneous at the same time. Therefore, forces of interaction are always present in a pair. Therefore, it is always present in a pair. It cannot act singly.